In the summer of 2022, the James Webb Space Telescope turned its golden mirror toward a patch of sky no larger than a grain of sand held at arm's length. Buried in that darkness was a faint smear of infrared light, stretched and reddened by its journey across the universe. When astronomers decoded it, they realized the light had left its source roughly 700 million years after the Big Bang. In cosmic terms, this was the universe, still in its infancy, barely 5% of its present age. The object, catalogued as QSO1, was not a star and not an ordinary galaxy. It was a quasar, the searing glow of matter falling into a black hole. And this black hole was wrong. Every measurement pointed to a mass of tens of millions of suns, packed into the heart of a galaxy that was tiny and chemically primitive, barely enriched with the elements forged in stellar furnaces. This should have been impossible. Black holes are supposed to grow slowly, accumulating mass over billions of years as they swallow gas and merge with their neighbors. Yet here was a monster that had reached that size in a few hundred million years, faster than our best models say it could. The galaxy around it was still young, still assembling, still poor in heavy elements, but its central engine already burned with the ferocity of a mature quasar. Astronomers checked and rechecked. The redshift held. The mass held. The paradox held. Something had appeared in the cosmic dawn that our physics struggles to explain. A giant born before there was time to build a giant. This single point of ancient light forces a confrontation with everything we assume about how black holes are seeded and how they feed. It suggests either that the universe made black holes in ways we have never confirmed, or that they grew at rates we thought forbidden. Before we can weigh those possibilities, we must understand how a telescope in orbit can read a message that is nearly 13 billion years old, and how astronomers know, with confidence, exactly when this impossible light was born. Light travels fast, but not infinitely fast. It crosses the distance from the Sun to Earth in about 8 minutes, and from the nearest star in over 4 years. Stretch that principle across the cosmos, and something remarkable follows. To look far away is to look back in time. When Webb captures photons from QSO1, it is not seeing the object as it is now. It is seeing light that departed nearly 13 billion years ago, a fossil image of an infant universe. But distance alone is not enough. Astronomers need to know precisely how far and therefore how long ago. Their key is redshift. The universe has been expanding since the Big Bang, and as space itself stretches, the wavelengths of light traveling through it stretch too. Blue light slides toward red. Red light slides into the infrared. The greater the redshift, the longer the light has traveled, and the earlier in cosmic history it was emitted. QSO1 sits at a redshift above 7, meaning its light was stretched by more than a factor of 8. Every recognizable fingerprint in its spectrum, the emission lines of hydrogen and other elements, has been shifted far from where we would see them nearby. This is precisely why Webb was built to see in infrared. Earlier telescopes, tuned to visible light, were blind to these ancient signals, because the universe's expansion had dragged them out of view. Webb's instruments catch that stretch glow and split it into a spectrum, a barcode of the object's chemistry, motion, and distance. From the position of those shifted lines, astronomers calculate a redshift, and from the redshift, they derive an age, 700 million years after the Big Bang. This is not guesswork. It is the same physics that governs a passing siren dropping in pitch, applied to the fabric of the cosmos. With the date locked in, the mystery sharpens. We know when QSO1 shone. Now we must understand what it actually is, how a feeding black hole announces itself across such distances, and how astronomers can weigh something they will never touch or see directly. A black hole itself emits nothing. It is a region where gravity is so extreme that not even light escapes. Yet quasars are among the brightest objects in the universe. The paradox resolves in the region just outside the point of no return. As gas spirals inward, it does not fall straight down. It forms a flattened, whirling disk, an accretion disk, orbiting the black hole at tremendous speeds. Friction and compression heat this disk to hundreds of thousands of degrees, and it blazes across the spectrum, from radio waves to X-rays. The light we detect from QS01 is not the black hole. It is the death glow of matter in its final orbits before vanishing. This is how a black hole betrays its presence and its size across 13 billion years. The brighter and more energetic the disk, the more mass it can reveal. Astronomers weigh these distant giants using the light itself. The broad emission lines in the spectrum come from gas clouds whipping around the black hole at high velocity. The width of those lines encodes the speed of that gas, and speed, combined with the size of the region, reveals the gravitational mass at the center. Apply this method to QS01, and the number that emerges is staggering: tens of millions of solar masses. What makes this system so unsettling is its setting. The host galaxy is small and compact, and its spectrum shows it is chemically primitive, poor in the heavy elements that generations of stars normally produce. In the nearby universe, such enormous black holes live in massive, evolved galaxies rich in processed material. QS01 breaks that pairing. It is a monstrous heart inside an immature body, a fully grown engine in a galaxy that has barely begun to build itself. The disk burns fiercely, the mass is confirmed, and the contradiction becomes physical rather than abstract. A black hole this heavy needed either an enormous head start or an extraordinary appetite. Neither comes easily under standard theory. To see just how severe the conflict is, we must confront the clock and the strict speed limit that governs how fast any black hole is allowed to grow. The standard story of black hole birth begins with a dying star. When a massive star exhausts its fuel, its core collapses, and if it is heavy enough, it forms a black hole. In the early universe, the first stars were giants, and their collapse might have left seeds of perhaps 100 to a few hundred solar masses. These are the ordinary building blocks. To reach QS01's mass, one of these stellar seeds would have to multiply its weight by hundreds of thousands of times, and it would have to do so within a few 100 million years. There is not enough time. The obstacle is not merely a shortage of gas. It is a fundamental limit on how fast anything can feed. As matter falls onto a black hole, the accretion disk grows brighter. But that radiation pushes outward, and infalling gas feels the pressure. At a certain intensity, the outward push of light balances the inward pull of gravity, and further gas is blown away before it can be swallowed. This balance point is the Eddington limit, and it sets a maximum rate of growth. Under the Eddington limit, a black hole grows exponentially, but with a fixed doubling time of roughly tens of millions of years. Start with 100 solar masses at the moment the first stars die, and even feeding continuously at the maximum allowed rate, you struggle to reach tens of millions of solar masses by 700 million years after the Big Bang. The seed simply cannot catch up, and this assumes ideal conditions: an uninterrupted supply of gas, no disruptive mergers, no episodes where feeding stalls. Real black holes rarely eat so cleanly. Every pause, every ejection of gas, every violent burst that scatters the fuel adds time the universe did not have. So the crisis is sharp and quantitative. The clock started at the Big Bang. The first stars needed a few 100 million years to form and die. That leaves only a narrow window for growth, and the Eddington limit slams that window nearly shut. QS01 should not be as heavy as it is. And then Webb found something worse: a black hole, even earlier, even harder to explain. If QS01 strained the models, the next discovery threatened to break them. As Webb continued surveying the deep sky, astronomers identified another actively growing black hole. Its light emitted only about 570 million years after the Big Bang. That is more than 100 million years earlier than QS01, and in the tightly constrained arithmetic of black hole growth, 100 million years is enormous. It is several doubling times stolen from an already impossible schedule. This object, like QS01, revealed itself through the telltale signatures of accretion, broad emission lines betraying gas swirling at high velocity, and a spectrum shifted deep into the infrared by the expansion of the universe. Its redshift placed it firmly in the cosmic dawn, when the first galaxies were still faint sparks and the intergalactic medium had barely begun to clear. Yet already, at its center, matter was falling into a black hole massive enough to shine across the entire observable universe. Push the calculation back to this earlier date, and the timing problem does not merely worsen, it becomes acute. The first stars could only have formed once gravity had gathered enough gas, a process requiring a couple 100 million years. From their death to this observed black hole, the available growth window shrinks toward a bare few 100 million years. Feeding at the Eddington limit the entire time, without a single pause, a stellar seed still falls short. The universe is presenting not one anomaly, but a pattern. These are not isolated flukes at the edge of measurement. Webb is finding early, heavy, actively feeding black holes repeatedly, in different fields of the sky, at different distances, all clustered impossibly close to the beginning. Each new detection tightens the deadline and narrows the escape routes. Either black holes were born far larger than dying stars could make them, or they fed far faster than the rules permit, or they came from something else entirely, something that predates stars altogether. The pattern demands a solution, and 3 candidates now stand forward. The first proposes that these giants never began as small seeds at all, but collapsed directly, in a single catastrophic event, from vast clouds of primordial gas. If a black hole cannot grow fast enough from a stellar corpse, perhaps it never started as one. This is the promise of the direct collapse black hole, a seed born not from death, but from a single, catastrophic surrender of gas to gravity. Imagine a cloud of pristine hydrogen in the first 200 million years of cosmic history, weighing perhaps 100,000 solar masses. Normally, such a cloud would fragment, cooling, splintering into 100 smaller stars. But if that cooling can be suppressed, the cloud stays hot, stays whole, and falls inward as one enormous body. Instead of scattering into starlight, it collapses directly into a black hole of 10,000 to 100,000 solar masses. Start from that, and the timing problem softens dramatically. A seed born already this heavy has a head start of thousands of times over a stellar remnant. Feeding steadily at the Eddington limit, it could reach the tens of millions of solar masses we see in QS01, with time to spare within 700 million years. The bookkeeping finally balances. But nature does not hand out such seeds freely. The recipe demands rare conditions. The gas must be chemically primitive, almost pure hydrogen and helium, because even a trace of heavier elements or molecular hydrogen would let it cool, fragment, and form ordinary stars instead. It also requires a nearby source of intense ultraviolet radiation to destroy those cooling molecules, a neighboring galaxy blazing at just the right moment and just the right distance. Both conditions together in the same place at the same time are thought to be genuinely uncommon. So the heavy seed solution buys us mass at the cost of rarity. Direct collapse black holes may explain a scattered handful of early giants, but can they account for everyone we keep finding? And if the universe simply could not manufacture enough of these exotic cradles, we are forced back toward the same monster from another angle. What if the seed was ordinary after all, but the feeding was not? What if these black holes broke the speed limit entirely, gorging faster than the rules were ever supposed to allow? The Eddington limit is not a law carved into the cosmos. It is a balance, a truce between two forces. Gravity pulls gas inward. The radiation that gas emits as it heats pushes outward. When the outward push equals the inward pull, growth stalls. That equilibrium sets the classic maximum feeding rate. But equilibrium can be broken. Super Eddington accretion imagines a black hole gorging far beyond this ceiling, swallowing matter in violent bursts that briefly exceed the limit by factors of 10, even 100. The trick lies in geometry. If gas floods in fast enough, it forms a thick, swollen disk that traps its own radiation, funneling escaping light into narrow polar channels while matter continues pouring in through the crowded equator. The photons that should have halted the feast are simply carried down with the flow before they can push back. Under these conditions, a modest stellar seed of 100 solar masses might not need to break any physics at all. It only needs to feast, greedily and repeatedly, during the gas-rich chaos of the early universe, where dense fuel surrounded every young black hole. A few dozen episodes of such runaway feeding, each lasting only a short cosmic moment, could bridge the gap between an ordinary corpse and a monster of tens of millions of solar masses by 570 million years. The appeal is that it needs no exotic seed, only extreme appetite. The objections are equally serious. Sustained super-Eddington feeding is difficult to maintain. The radiation pressure and powerful winds it generates tend to blow away the very gas the black hole is trying to consume, choking off its own supply. Whether a black hole can keep gorging long enough, often enough, remains hotly contested. And so we have two competing rescues, a heavy seed or a hungry one, each straining to explain the same impossible timing. But suppose both are wrong. Suppose these black holes did not form from stars, or from collapsing clouds, or from anything in the era of galaxies at all. Suppose they were already there, waiting, long before the first star ever shone. Rewind past the first galaxies, past the first stars, back to the universe's opening second. Here lies the most radical explanation of all: primordial black holes. In this picture, some of these early giants were never seeded by anything that lived. They condensed directly out of the newborn cosmos, in the first fraction of a second after the Big Bang, from regions where the density of the fireball fluctuated just slightly higher than everywhere else. Where matter was packed dense enough, gravity could collapse it on the spot, forging black holes before atoms existed, before nuclei fully formed, before there was any light at all. The appeal is immediate. A primordial black hole does not need to race against the clock, because it was there from the very beginning. It could have spent the entire first billion years growing, accumulating gas across hundreds of millions of years, sidestepping the timing problem completely. Some theories even suggest they could seed the supermassive black holes at the hearts of galaxies, threading a hidden lineage from the universe's first instant to the quasars Webb now detects at redshifts beyond 10. Primordial black holes carry a second temptation too. They have long been proposed as candidates for dark matter, the invisible mass that outweighs ordinary matter 5 to 1. To explain both the early giants and the dark cosmos with a single population would be an extraordinary economy of ideas, but temptation is not evidence. Not a single primordial black hole has ever been confirmed. Their existence depends on assumptions about density fluctuations in the earliest universe that we cannot directly test, and observational limits have steadily squeezed the mass ranges they could occupy. They remain a possibility, elegant and unproven, hovering at the edge of respectable physics. So we arrive at three answers to one question, each partial, each contested. Heavy seeds from collapsing gas, runaway super-Eddington feeding, relics from before the stars. Each explains something, none explains everything. And that leaves us standing before the deepest question of all, the one these discoveries force us to confront directly. So which is it? We have three candidates on the table, and the honest answer is that we do not yet know. Direct collapse seeds solve the mass problem, but demand rare, pristine conditions that may not have existed often enough. Super-Eddington feeding needs no exotic cradle, but strains to sustain itself against its own violent winds. Primordial black holes escape the timing problem entirely, but remain, to this day, entirely unconfirmed. Each explanation fits some of the evidence and stumbles on the rest. The universe has handed us a puzzle whose pieces come from three different boxes. What settles it will be observation, not argument. The James Webb Space Telescope is only beginning its census of the first billion years, and every new detection sharpens the picture. If astronomers keep finding black holes that are too massive relative to their host galaxies, that lopsided ratio favors heavy seeds, because a black hole born large would outweigh its slowly assembling galaxy. If instead we catch black holes in the act of feeding beyond the Eddington limit, glowing with the signature of trapped radiation and blistering outflows, the hungry seed model gains ground. And if a population of black holes turns up with masses and distributions that no stellar process can explain, the primordial idea may finally step out of speculation. Future instruments will join the hunt. Gravitational wave observatories may one day detect the mergers of these early giants, reading their masses directly from ripples in spacetime. X-ray telescopes will probe the hot gas swirling into their accretion disks. Each measurement narrows the field, ruling out what cannot be while illuminating what remains. What is certain is that objects like QS01 and the growing black holes seen just 570 million years after the Big Bang have already broken the tidy story we told ourselves about how cosmic structure assembles. They are not anomalies to be explained away. They are signposts, forcing us to rewrite the earliest chapters of cosmic history. Whatever the final answer proves to be, the message these ancient lights carry across 13 billion years is unmistakable, and it changes everything. The first giants came too soon.